Welcome to a fascinating journey into the mathematical representation of radioactive decay and the possible existing time of radiation. In this video, we'll explore how nuclear physicists use elegant equations to describe the spontaneous disintegration of radioactive substances, and we'll uncover a crucial, often overlooked concept that deepens our understanding of how radiation behaves over time. Whether you're a student, a science enthusiast, or just curious about the invisible forces shaping our universe, this exploration will reveal the hidden patterns governing atomic decay. Radioactive decay is a natural process where unstable atomic nuclei lose energy by emitting ionizing radiation. This transformation is spontaneous, meaning it happens without external influence and is a cornerstone of nuclear physics. When a nucleus decays, it changes into a different element or isotope, releasing energy in the form of particles or electromagnetic waves. This process not only shapes the elements found in nature but also has practical implications in medicine, energy, and environmental science. Mathematical law of radioactive decay is beautifully simple yet powerful. It's expressed as n equals n0 e minus lambda, where n is the number of undecayed nuclei at time t, n0 is the original number and lambda is the decay constant. This equation allows scientists to predict how much of a substance remains after a given time, forming the backbone of nuclear physics calculations. However, as we'll see, there's more to the story than this classic formula. While the decay law is fundamental, it doesn't capture every nuance of radioactive processes. There's a missing piece, a mathematical series that describes the sequence of decay events over time. By introducing this concept, we can better understand not just how much of a substance remains, but the order and timing of each radiation emission. This deeper insight helps bridge the gap between simple equations and the complex reality of atomic transformation. Decay series is a mathematical representation of the sequence in which a radioactive substance emits radiation. It's not just about the total number of nuclei left, but about the order in which each decay event occurs. By examining the series, we can track how a substance transitions through multiple stages, each with its own emission and transformation. This approach reveals patterns that the basic decay law alone can't show. Let's break down the math behind the decay series. Starting from the decay law, we derive several forms. Nn0 equals E minus lambda, lnn slash n0, minus lambda and lnn slash n equals lambda. For a fully decayed substance, the product of the decay constant and time equals 1. This means that the logarithmic ratio of original to remaining nuclei gives us a direct measure of the decay process's progress. The concept of order of decay, represented by m, is introduced to track how many times a substance has emitted radiation. For the first emission, m equals 1, for the second, m equals 2, and so on. This order helps us understand the sequence and timing of decay events, providing a richer picture than simply knowing how much of the substance remains. Half-life is the time required for half of the radioactive nuclei in a sample to decay. The number of nuclei after time t can be written as n equals n0 slash 2n, where n is the ratio of time elapsed to the half-life. This formula connects the abstract decay law to real-world measurements, making it easier to predict how substances change over time. By combining the concepts of order of decay and half-life, we arrive at a powerful equation. ln n slash n equals 1m. This equation allows us to calculate the order of decay for any stage, linking the mathematical series to physical reality. It's a tool for tracking the step-by-step transformation of radioactive substances. In the decay series equation, the value 1 represents the unity of the substance before decay begins, while 0 represents the completion of the decay process. This simple but profound idea helps us visualize the entire journey from a fully intact nucleus to its final transformation, emphasizing the continuous nature of radioactive decay. Every radioactive decay follows a specific pattern described by the decay series equation. The order of decay m and the ratio of time to half-life n together determine how the process unfolds. This mathematical structure ensures that each disintegration event fits into a predictable sequence governed by the laws of physics. Now let's turn to a key question. How long does emitted radiation actually exist? The duration depends on the properties of the radioactive substance and the nature of the emission. Understanding this time frame is crucial for safety, medical applications, and environmental monitoring. Heisenberg's uncertainty principle provides a mathematical foundation for the duration of radiation. It states that the product of the uncertainty in energy and the uncertainty in time is at least half of Planck's constant. This principle sets a fundamental limit on how precisely we can know both the energy and the duration of a radiation event. When a substance emits radiation, it also vibrates. The energy of the released radiation equals the vibrational energy of the substance, which is determined by its vibrational frequency. This connection links the microscopic motion of atoms to the macroscopic effects of radiation. By applying the uncertainty principle and the concept of vibrational energy, we derive a formula for the possible existing time of radiation, T equals 1 slash 4 pi vibrational. This equation shows that the duration of radiation is inversely related to the vibrational frequency of the emitting substance. Vibrational frequency itself can be calculated using the decay constant and the logarithmic difference between original and remaining nuclei. F vibrational equals lambda slash 4 pi ln n0 minus n. This formula ties together the physical properties of the substance with the mathematical framework of decay. By substituting the vibrational frequency into the duration formula, we get T equals minus n slash lambda. This equation allows us to estimate how long radiation persists after emission based on measurable properties of the substance. It's a practical tool for scientists and engineers working with radioactive materials. Knowing the possible existing time of radiation helps us design better protection strategies. By understanding when and how long radiation is present, we can minimize exposure and safeguard health. This knowledge is essential in fields like nuclear medicine, power generation, and environmental cleanup. Mathematical tools developed for radioactive decay have wide-ranging applications. From dating ancient artifacts to powering spacecraft, understanding decay and radiation duration is crucial. These equations also inform research in astrophysics, geology, and even biology, wherever radioactive processes play a role. Let's recap the key equations. The classic decay law n equals n0 e minus lambda, the decay series equation ln n slash n equals 1m, and the duration formula T equals minus n slash lambda. Together, these tools provide a comprehensive framework for understanding and predicting radioactive decay and the persistence of radiation. Conclusion: the mathematical representation of decay and the possible existing time of radiation offer powerful insights into the atomic world. By integrating classic equations with new concepts like the decay series, we gain a deeper, more nuanced understanding of radioactive processes. As research continues, these mathematical tools will remain essential for advancing science, technology, and safety in our ever-evolving world.